Hi again, everybody, and welcome. Today is Monday, May 3rd. Today is again the deadline for applying for this grant, the California Space Grant Consortium, which is really cooperation between NASA and actually UCSD, University of California, San Diego. And hopefully some of you already have applied, others they would consider applying as soon as possible. And we have quite a few things that probably we can do. Again, one of them is, and it's up to you guys, and we're going to discuss that the minute that this is finalized, basically on several ideas, either drones or Arduino boards. I have my Arduino board in here. Actually, I have an Arduino robot in here. I thought maybe you guys can see. So what it's made up of, it has the wheels, of course, and servo motors. And let's see if I can put this stuff out a little bit. There is the stuff that goes with it. And this is for the chassis, basically. And also, so many components and sensors underneath. And there are two main controllers. One of them is actually the Arduino board itself, which is a controller in here. Let me see if I can see it. That's not it. I don't think this is the one, but it looks like this one actually. And some of them are actually, I think that's the one. Yeah, I took it out. It was in this. That's the main Arduino board. And this is the newer version, version 3 actually. I have both versions. There's so many sensors, so many stuff in here that needs to go, including a remote actually. But again, this is one thing that potentially we could do. And that is Arduino boards, basically Arduino things like this one. This is where the battery holder is, because you would want it to automate. You would want to put the battery in and the car starts to move on its own, fully automated. To program it, this one is C++, okay? I know the DJI basically drones, they require actually one of the two programming languages, either a native programming language, which is like a GUI thing, I mean, you draw the stuff that you wanted to be executed, or you use Python for it, okay? And also, so we have a drone, we have this one, and we also have a Raspberry Pi, which is also another way of doing it, that you load your actual programming language. And you also build stuff like this one. You build the robots, basically, or you build a whole car, basically, that can achieve whatever goals you have in there. Anyway, so these are some of the things that I'm hoping that you guys can join on. The theme, again, is by NASA. It has to be related to corona virus, or actually a lunar mission, okay? So one of the two. So, but when we had a meeting last time, because I wanted to clarify on this one, they said it's really not a requirement in a sense. If our students would want to do something different, they can do that. So it's not really a required thing. As long as they are ready to present it in front of a panel of scientists and engineers, okay, and basically show what they have done and explain things that what they have done and all of that. So I think it's a fun thing. So I'm hoping that those who did not apply yet, they still have until the end of the day to apply, and that way we will get them in, okay? So that's one thing. The other thing also in terms of the class today, actually we're doing chapter 29. I know we did chapter 28. We have still chapter 29 and chapter 30. Chapter 29, chapter 30, they're really one idea together, okay? So I'm probably going to combine them together in terms of the thoughts. I'm probably going to do a problem today from chapter 29, because it's quite a work actually to do that problem. And then we're going to jump into the induction, and we get a break basically in terms of applications from these two chapters. And then we get to the AC circuit, which is really the next two chapters, 30 and 31. I mean, sorry, 31 is for the AC circuits. And chapter 32 is independent of everything else. Chapter 32 is this basically big synthesis of everything. We put everything together in just one big chapter, okay? So that's really where we're headed with this class. So let me jump into my notes in here, share. Bring this closer in here. So chapter 29 deals with an idea. Here is where we are right now. Let's see where we stand so far. When we started this class, if you guys remember, we said that we wanted to understand phenomena related to electricity and magnetism. For that, we developed the field theory. And the first thing we said that the electric field was the first concept that we explored, and the electric field is created by charges. So if you bring another charge inside an electric field, it's going to be subject to a force, basically, okay? Where that force is going to be QE. So now I need to find what this electric field is. So for that, we said the divergence, or the flux of the electric field over a closed path, closed surface, sorry. Flux is over a surface, not over a path, of E dA is simply the measure of the charges enclosed divided by epsilon naught, okay? There is another way of saying the same thing, which is exactly equivalent to this one. We could have said the divergence of the electric field. This is the operator del. The del operator in here is just the derivative with respect to x in the I hat direction, the derivative with respect to y in the j hat direction, and the derivative with respect to the z direction, the z variable in the k hat direction. So just an operator is equal to the charge distribution divided by epsilon naught. It's the same thing, okay? Use the divergence theorem. So this requires a little bit of vector calculus to show it, but it's the same identity. Now we said also that the magnetic field never diverges, meaning if I look for the divergence over this magnetic field over a closed surface, this must be equal to 0. Again, why is that? Because the magnetic field always leaves an area and come back to it. So in other words, it goes around and come back to it, so there are no monopoles, so this must be 0. In other words, there is no source of the magnetic field in a sense like it gives you like monopoles, gives you like, for example, positive field lines emanating from it, like the electric field. The electric field, you could have a charge, positive charge in here, and the electric field will leave it in all of the directions. So when you look for the flux of the electric field in that region, it's basically the density of this line, the number of this lines per unit area, that's it. And that is expressed in terms of the charge over this constant, which is epsilon naught. That has to do with the medium. The magnetic field goes around and comes back. So if you're trying to find its flux over this area, well, the field will leave but come back, and then it leaves again and comes back. So it's always 0, no matter how much you count it. If you count some of them positive, others negative, so it's going to always 0. And that is because there are no monopoles, really, no monopoles. And like the electric field, the electric charges, they can be positive by themselves and negative by themselves. You can separate the charges in here. So there are monopoles in here, okay? But in here you can't. So therefore, this one is equivalent to saying that the magnetic field does not diverge. So this is so far what we know in terms of surface areas. In terms of what we know in terms of the line integrals, then we also found that the line integral over a closed path now of the magnetic field B dl is simply equal to mu naught times the current enclosed. And this is, in a sense, what causes magnetic field to begin with. So the magnetic field will circulate, so it's going to go in circles like we have predicted from the previous relationships, and that circulation is a measure of how much currents are going in and out, okay? So if I have a measure for this one in terms of current densities, I could write this one using actually the Stokes theorem, and Stokes theorem will tell me that the circulation of the magnetic field is simply equal to mu naught times J, where J is the current density. In other words, what that does for me is it converts this line integral. So this is Stokes theorem. Again, this is stuff from vector calculus. You're really not supposed to know it at this point. I mean, the proof for it is not really hard, honestly, but you can use that to show that this one variable integral becomes a two variable integral over the same area where the current is distributed with the current with distribution J. So this relationship and this ones are the same thing. Your STEM coordinator, she's calling me right now and I cannot talk to her. So I'm going to tell her, yeah, because probably she's telling me about some of you who applied for the grant already. Anyway, the point being in here is that these two expressions are identical. So this is what we know. However, if you guys remember, the electric current, this current itself, is caused by an electric field. Because in a wire, conducting wire, there are charges anyway. If I apply potential, so if this is a V1 and a V2, so that V2 is more than V1, for example, then in this case, charges starts to move. The higher potential to the lower potential. I'm sorry, they move this way. Okay. So the charges move that way because I assume V2 is more than. Anyway, so there is an electric field in here that causes their motion because the electric field and the difference of potential are related to one another. And remember, E is equal to minus grad of V. So if I apply difference in potential, then in this case, I have an electric field that causes that difference in potential. So the current in here is caused by the electric field in a sense. So the electric field, this is Ampere's law, by the way. This is the last one that we did last time. So Ampere's law, really what it says is an electric field, which creates a current, creates a magnetic field. Because this is exactly what this expression is saying. So here is the deal. In order to have a magnetic field, you need an electric field. An electric field generates, and directly, of course, generates a B field. So people were saying, okay, it looks like it's very, very symmetrical what's going on between the electric field and the magnetic field. It looks like everything that we see in here looks like there are parallels in here and so on and so forth. Could it be that the magnetic field creates an electric field? So that's the question that was facing the scientists in the early of the 1900s, basically 20th century. I mean, what is it? The 1800s, I'm sorry, the 19th century. So here is a question. Could it be that B also does the same thing for an E field? Can I make an electric field out of a magnetic field? So that is really the challenge that they have, that they were facing. So I'm going to switch cameras to show you the experiment that I have in here. And so let me stop sharing to see if it's possible for me to generate an electric field. Remember, an electric field across a wire will generate a current using nothing but a magnet. Okay, so I'm going to change cameras. Where is the camera thing? Here is the camera thing. Oops, I turned it off completely. I didn't mean to do that. Okay, I probably have to turn on the light a little bit, at least in that angle, because for lighting in that camera. Okay, so let's see here how this looks like now. Okay, a little bit better. Okay, so what I have in here, I have a wire. So this is a wire by itself, okay? And I mean, it's so many turns in here, and there are no other things in it. There are no magnet. This is actually not magnetic at all. So if I try to put a magnet next to it, nothing is happening in here. Nothing is happening. There is no interaction, no repulsion. And so if it was repelling, if it was attracting this way, if I flip it, it should repel, and it doesn't do any. So actually, this is a material that is non-magnetic. Okay. So, and now I have actually a multimeter in here where this is connected in. There is nothing in my circuit in here other than this one. So I'm going to turn the multimeter, as you can clearly see, it's in the current position. So I'm going to turn it to detect tiny currents. Right now there is no currents, okay? Unless I bring a magnet and put it in my circuit. Obviously, as you can clearly see in here, there is no current either. So magnetism cannot create an electric field, unlike, for example, what Ampere's law is saying. Ampere's law is saying that an electric field will create a magnetic field. As long as you have a current running through a wire, it's going to create one. Obviously, if this moves, it looks like it's interacting, as you can clearly see in here. So let me remove this thing. It's attached to all of these things in here. So you're still seeing that, but let me see. Again, as long as I don't move this, nothing. But if I move the magnet out or in, you will see that there is a current. As long as the magnet is moving in or out of the wire, then I have, in this case, a current. Now, what happens if I don't move the magnet, but rather I move the wire itself? It's the same thing. So as long as there is a motion, either the wire moving in and out or the magnet moving in and out, actually I have a current, as you can clearly see from the multimeter. There is another way of doing it, but I cannot really show that, because if I change the value of the magnetic field itself, it's going to also do the same thing. So that is basically, in a nutshell, what this experiment is. Let's turn this one, and let me switch cameras again. So what this demonstration illustrates is the following. You cannot create a magnetic field, an electric field out of a magnet. You have to have the magnet moving with respect to the wire in or out, or the wire moving in and out with respect to the magnet, or both. Of course, we can move both of them. Or there is another third option that I cannot demonstrate to you guys, and that is to change the magnetic field. Don't move neither. Keep the magnet in its place, keep the wire in its place, but change just the magnetic field, that's it. Change it from whatever value is, keep on increasing it or decreasing it, change it. As long as you change it, then in this case also, you're gonna achieve the same thing. So let me illustrate this one. Let me share the screen again. Illustrate this one with the following experiment, basically. So what I have in here, let's say, for example, the direction of the magnetic field is pointing into the screen. And let's draw the magnetic field with some different color. Okay, so, oops, I still blue. I wanted blue. Okay, so let's draw the magnetic field in this, going into the screen, okay? In a region of space where the magnetic field, in other words, the north is this way and the south behind the screen on the other side of the screen. Obviously, if I do this and move the wire in and out, what I'm doing, actually, I have more field lines coming in or coming out. If I move in, more field lines going in. If I move out, more field lines actually receding from the wire. Okay, so that's exactly what I was doing earlier. But instead of doing that, this is what I'm going to do. I'm going to take a wire. Let me make it thicker a little bit, okay? And draw a wire in here. And attach to it a light bulb. This is a hypothetical, of course. I'm not going to attach a multimeter to it. I'm going to attach a light bulb. And here is my wire. Partially submerged inside the magnetic field. So the magnetic field is going into the screen. And the wire, as you can clearly see, is partly inside that, inside the magnet. What I'm going to do, actually, I'm going to move the wire. So this is similar to the second part that I demoed for you guys. So I'm going to move the wire with a certain velocity v, okay? And what I'm going to say in this case is, I should see that light bulb go on. In other words, there will be a current running through the wire, okay? As long as it's partly submerged, partly immersed inside the magnetic field. If it's fully immersed, I should not see the light bulb going on. If it's not partly basically immersed, if it's completely out, then also the light bulb will not go on. So this is actually what the observation is saying in here. So that is in a nutshell what the essence of this experiment that I showed you earlier demonstrate, in the sense that there is actually current that is going to flow through the circuit. So there is a magnetic field in this region. So one, it is partly immersed inside the magnetic field. So what's going on in here? This is how much it is, by this much at this point. This is how much it is. So if I measure this quantity, which is the magnetic field, in this case B, times this area, that is the flux of the magnetic field. So the flux of the magnetic field in this case is going to be simply equal to, I have to put it B, which is just B times the area in this case. And the area is clearly what's going on in this case. If I take this one, the width W, and the length L, so in this case, what is this area in here? It's just W times this much only, not the whole L, because I need to just find the overlap. And the overlap in this case is just this value, which I'm going to call X. So it's B times W times X. X is changing at the rate of V. As a matter of fact, V is equal to dx over dt, because it's moving in. And as it's moving in, the area is getting bigger and bigger. The flux is increasing in the inward direction. I'm encountering more and more field lines pointing into the screen. Okay. So the flux is increasing, and now let me see what's going on charge by charge. The charges, the individual charges themselves. If I look at charge sitting in here, Q, that charge is moving this way, and the magnetic field is coming into the screen. Into the screen, so I cannot really draw it. It's really in X. Okay, so the force, if I use QV cross B, so I have V is this way, B is into the screen, so the force now tries to pull this charge out of the material, tries to pull it this way. If I take a charge in the same direction in here, the charge is still moving this way, the magnetic field is still going into the screen. So again, that force is trying to lift the charge out of the wire. And as long as this force is not big enough, charges cannot jump out of the material. So I'm assuming that the wire is rigid now. So this will not do anything. However, a charge sitting in here, Q, it's moving with the velocity V this way. And inside the magnetic field that is into the picture. So it's moving this way, and same thing. So this will move by this force pointing upward, and that will move because it has room to move. It can move through a wire, which is assumed to be conducting wire. So this charge will move because of this force here. The charge that was here will come and replace it. The charge that was here come and replace it. Now, because this is a conductor, there is a charge that was in here will come and replace it. Remember, charges do not belong to anybody. They belong to the community of charges, and so on and so forth. So this charge will come and replace this one, and this one will remove this one, this one. The one that moves in here needs to push this one to the forward, and this one actually is moving forward because of the same effect. This one actually moves in here. Now there is an excess of charges in here because it's a conductor and it needs to stay neutral. So the charge that came in here needs to push this one in there. And now I have actually established the current that is going to go clockwise. I mean, counterclockwise. So the current is actually going to flow in this direction. And that is what causes the light bulb to go on. Okay. So here, we actually, all we needed was QV cross B. That's all. By the way, I'm sorry, let me fix something that I was intending to fix earlier in here. This law actually needs to be fixed in light of what we know now in terms of the magnetic field. So this force is only due to an electric field. Now, in the presence of the magnetic field, we have this force. So this force actually will explain what's going on in here. And at this point, we really don't need any more equation than these three equations so far. So we still have the equation number 1, which is a scalar equation, which is made up of only one equation. This equation number 2, which is also a scalar equation. Equation number 3, which is Ampere's law, is actually a vector equation. These are three components in the x direction and the y direction and the z direction. So far, really, if you break it down into its components, there are 3 plus 2 for a total of 5 equations. 5 equations, once you solve them, theoretically, you should be able to find the electric field and the magnetic field. However, I have the circulation of the magnetic field and the divergence of the magnetic field. I have both of them. So the magnetic field is well defined by these two equations, 2 and 3. However, the electric field is not really well defined because of this fact that this equation only tells you how it diverges. It doesn't tell you how it circulates. Is the circulation equal to 0? If it is 0, then that's fine. That's another equation. But the point being in here is that this thing in here is giving me circulation for the electric field because there is no battery in here whatsoever. So what I have actually done in here, I have created an electric field because that's the one that moves charges. And that electric field actually is circulating counterclockwise with no battery. I have a light bulb going on. Same thing that the experiment has shown. There was no battery whatsoever. All it did was change the magnetic field in and out. So that magnetic field has a circulation. And now, this is the missing link, if you wish. This is the equation that we really needed to find. The circulation, which is by definition the EMF of the battery, if it's a battery, for this one, it's acting as if it's a battery. The circulation of the electric field over this closed path is EDL, is equal to some battery. Well, the experiment has to do with the rate at which this flux is changing with time. If this does not change with time, if you keep like I showed in the beginning, if you keep the magnet sitting on top of the wire, nothing happens. You saw that the current was 0. As long as they are sitting next to one another, there was no motion. The only reason why you saw fluctuations is because I have a bunch of magnets. As a matter of fact, this one also has a magnet behind it to help you carry it. So this one actually carries with it a magnet. If we neglect all of the magnets that are other than that one, then, and I had actually other magnets sitting on the table too. So that's why you saw fluctuation. But I tried, and even then you saw that there was no current. And this multimeter was set up on this side, actually. I put it on the microamps. So it would have detected extremely small magnetic currents. So because of the fact that it was sitting on that extremely slow value of the current, and it did not detect it, that indeed, with no motion, no relative motion, or no change in the flux of the magnetic field, there was no EMF. There was no circulation of the electric field that caused that current. Therefore, this value, I'm going to leave a space in here, and you guys, hopefully you guys have your papers working with me too. So it's going to be a change in the flux of the magnetic field with respect to time. Okay. So that is the one expression here, because that is how the EMF is. I'm going to put a minus sign in here, and I will tell you exactly what that minus sign is coming from. Okay. Because let's focus just on the magnitude of this force in here, and let's see why is it that way. Okay. We know that these are charges Q moving in a magnetic field B with a velocity V. The EMF is actually how much energy it takes to move 1 Coulomb charge, 1 Coulomb charge. So the EMF is the energy to move 1 Coulomb charge. So 1 coulomb charge is subject to the force V cross B. Remember, the charge Q is equal to 1 by definition. Okay? So this is the force on 1 coulomb charge. Okay? And by the way that I wrote it, the way we wrote it in here, it's equal to V times B in magnitude, pointing in the y direction, pointing in this direction, pointing in this up direction in here. Okay? So this force now in magnitude is equal to V times B pointing upward. Because this force is always pointing upward, and if I want to find F times dl, which is the force times displacement, to find the energy it takes to move 1 coulomb, which is that force on 1 coulomb times the displacement. This product will cancel in here because the force is up this way and the displacement in here. So there is a cosine of 90 degrees, which is 0. The same thing in here. The force is up, dl is this way. So again, this is cosine of 90 degrees, which is 0. There is no force in here because you need a magnetic field to do V cross B, and there is B is equal to 0 in this region. So there is no force in here. There is no force in here. There is no force in here. The only place where there is a force other than this portion, and this portion is in here. And that F times dl is simply F times dl. Because both of them are in the same direction. The force is in this way and the dl in this way. And the force is constant on 1 charge, which is V. I'm assuming V is constant, B is constant. So in this case, the force is constant. So the integral from 0 to W will just give me the EMF now. EMF was simply equal to V times B, that is the force, times the displacement, which is W. Okay? And if you notice that the flux of the magnetic field, phi B, is simply equal to B times the area, and the area is X times W. And if you take the rate of which this is changing with time, the derivative of X is V, so I have BVW. And this is exactly this expression. So in terms of magnitude, this is correct. This experiment is correct. The trouble with it is the direction. The direction was wrong. I mean, I have to have a negative sign. That's my point. This sign must be negative. It cannot be positive. Let me explain why that is. Okay. The current is circulating. The current that resulted from this whole thing is going counterclockwise. So if it creates its own magnetic field, and it does, it's going to point out of the picture. Again, the current is going around the palm. If you use your palm, is going counterclockwise. So it's magnetic field, the magnetic field that it's made up, not the one that is that it has. So its own magnetic field. This is the induced magnetic field. I'm sorry, it should be pointing out of the picture. So it's coming out. Why? Because the current that it has been generated is going counterclockwise. So it has created its own magnetic field that is pointing against where the magnetic field that created it. So the magnetic field that created was going into the screen. This one generated an EMF, an electromotive force, which has a current, which has a magnetic field that circulates, number one. Number two, that circulation results in a magnetic field that compensates for the field lines that are going in. Because as you move the wire this way, more and more field lines are going in. So this will generate its own magnetic field to compensate for the ever increasing field lines going into the picture. So it's going to have more and more field lines coming out. Hence the negative sign. So it's really biting off of the hand that caused it to begin with. That is what the negative sign is in here. So this is the picture that emerged then. The circulation which is the EMF, by the way, of the electric field that was induced in here is equal to minus the rate at which the flux of the magnetic field is changing with time. This is called Faraday. Because Mr. Lenz is the one who explained that negative sign, we call it Faraday Lens Law. Okay. It's really a lot of things going on in this expression. First of all, we don't have any battery whatsoever. Yet the light went on. Yet, as you saw, also the ammeter registered the current in my circuit. I did not have any battery whatsoever, and that happened. So in this case, an EMF was created just because of the relative motion of the electric field and the magnetic field and the wire. That's all. In the opposite direction, also, I kept the wire fixed and I moved the magnet in and out. That created the same thing, because you might be tempted saying, okay, wait a minute. If the wire is moving, therefore, it's actually what matters is just the rate at which this area is changing. More field lines are coming in. If you move it in the opposite direction, if the wire were to move in the opposite direction, the current actually will go clockwise. Because if you move it out, you're taking less and less field lines going in. So in this case, the current will go clockwise to compensate for the ever decreasing number of field lines going in. So it's going to push more and more inside the screen. So that is the negative sign. The negative sign is always compensating. If you are increasing the field lines, it's going to decrease them. If you're decreasing them, it's going to increase them. That is the negative sign. It's opposing basically the reason that made it to be to begin with. Because there was no electric field, no electric current whatsoever if that magnet did not exist, if that flux did not exist. So the flux existed and then changed it. Because it's changing now, it's increasing in one direction, so it's going to create its own magnetic field to compensate for that flux. It's going to push it in the opposite direction. Obviously, it's kind of hard at times to even imagine this concept, especially since we are not sitting in a class and doing this experiment live and things like that. But hopefully it becomes clearer with the algebra when we do problems with it. The bottom line is we have discovered a way of creating current. And this is actually how we make current to begin with. This is how current is generated everywhere. I mean, with the generators. So that's how we make current. We make it this way, okay? We don't carry with us batteries all over the place. As a matter of fact, your car battery, if you just rely on the car battery, you're not going to go very far. You have an alternator in there, generator that generates electricity to recharge the battery all the time. And it takes from the motion of the car, basically from the engine, and converts it back into electricity using this principle. And you have a dynamo that is spinning, and that builds more charge back to the battery after you use it, after you start the car. So it's everywhere. This is the mechanism on how you make electricity. So in a sense, this is another way of making electricity. Now we could have done, and I did not, and I'm sorry I cannot, but we could have done this experiment in the following fashion. And that is because there's constraints in here. I really don't have access to the materials to do that, but hopefully you guys can understand in light of what we saw. So if I have a loop in here, and let's say, for example, again, I have a light bulb in here. Okay, and if I have a region of space that has, again, a magnet in that region, let me pick up the blue in here for the magnet, pointing into the screen again, and I'm taking the whole thing, it's fine. Submerging it into the magnet. Nothing is moving, neither the wire nor the loop. I mean, not the magnet or the wire. Both of them are sitting still. If that's the case, nothing is going to happen. The light bulb stays basically not lit. But if the magnetic field changes with time, either increase or decrease. It's increase meaning more field lines going in, decrease means less field lines going in. So in this case, the flux of the magnetic field still change, because the flux of the magnetic field over this area, if this is L and this is W, it's still the B times L times W. L is fixed, W is fixed, but B is changing now with time. So d phi over dt is not zero. which means that there is an EMF still in that case. The light will go on. This is the one that I cannot really demonstrate because I have permanent magnets, and permanent magnets, their magnetic field is fixed. You cannot change it, okay? So that is another way of actually getting an EMF too. So the moral of the story is, and this is actually an experimental law, of course, we're talking about experiments. This is not a something you ask me to prove, is that the changing of the flux of the magnetic field with the negative sign will generate an EMF. An EMF, you can write it as the circulation of the electric field. So we have something weird that happened right now. This electric field is circulating because its circulation is not zero. Okay, it's equal to the negative of the derivative of the flux. The flux of the magnetic field in general, for this simple geometry, is simply the area times the magnetic field. But in general, it's the integral of BdA. So what we ended up with is another equation to the already three equations that I wrote before. And this equation says the following, that the circulation of EDL is minus the derivative with respect to time of the flux of the magnetic field. If I take, again, Stokes Theorem, I can convert this single integral into a double integral. And I will pull the curl of the electric field. And then this is already a double integral. And for these two double integrals to be true all the time, the integrands must be the same. And then I will pick up the partial derivative of b with respect to time. So this is equation 4, if you wish, whether in this form or that form, it's the same equation that gives me, so using Stokes theorem. So if you don't worry about the how you get this thing in here, but the point being in here is this is how it's sometimes you're going to find it, okay? It looks like we have a good picture now. It looks like we're in good shape because theoretically at this point, we have found how the electric field diverges. And its divergence depends on the charges enclosed. How the electric field circulates, and its circulation depends on how the magnetic field changes with time. We found how the magnetic field diverges, and it never does because there are no monopoles. Okay. We found also how the magnetic field circulates, and it circulates depending on the currents enclosed. This is Ampere's law. The last one I mentioned is Ampere's law. This is the equation that I wrote is Faraday Lens Law. When we come down to chapter 32, or actually before that probably, we will see that there is something the matter with the Ampere's law. There's something flawed in it. We need to fix it. Mr. Maxwell fixed it and it became his and Ampere's law. Now it's named after, it's fixed, of course, as being Ampere-Maxwell's law. And that is everything that we learn. That is everything that we would have learned by now. So we are almost there. We are almost where we need to be. If we fix this equation, equation 3, where is it? This one, if we fix it, either in this form or that form, it doesn't matter which, we're in good shape. Then we would have discovered everything and we know everything about electricity and magnetism. Add to it this equation, Lorentz force, which is equation 5 if you wish. You can solve any problem. Add to it F equals to ma. Then you know everything there is to know about electricity and magnetism and how to solve it. Add to it another equation that I'm going to probably, what is this thing in here? Another equation that you have seen from physics 4a, and that is the force between two charges, between two masses, m1 and m2, is given by this expression. Then that's everything you know up to this point. Everything we know up to this point in physics can be summarized by this bunch of equations. The gravitational force, the 4 equations of Maxwell, the one that I listed, Lorentz force, that's it, that's all you need. And F equals to ma, Newton's force, Newton's law of second law of motion. That's everything, the entire thing. There is actually, Mr. Feynman has a summary of it in his book, one of the volumes. I don't remember which one it is. I have all of 3 volumes in here. He summarizes them all in one table. And it's really worth remembering all of these things. That's everything that we know up to that point, okay? Barring modern physics, barring relativity, basically. And even if we include relativity, it would not really be that much. We can just change the momentum and the second law of second law of Newton. Instead of writing it F equals to ma, we write it F equals to the change of momentum with respect to time, and redefine the momentum using the gamma factor. And then after that, everything we know about physics up to that point without quantum mechanics can be summarized. So all you need to do is just change this expression a little, which you saw actually in physics 4a. This can be written as the change in momentum with respect to time. The only thing in here in relativity, you have to change the definition of the momentum. Actually, the momentum has a some factor that needs to change. It's not just mv, it's mv times gamma, or mv divided by square root of 1 minus v squared over c squared. Once that's done, then that's everything you need to know about physics, actually, up to that point, prior to quantum mechanics, prior to the advent of quantum mechanics. So this is interesting because today, actually, we came to the culmination of everything. We reached the top of where we need to be, actually, with Faraday's Lens Law, because we have discovered basically one of the last secrets in classical mechanics, this one. Obviously, like I said, there was something the matter with this expression that needs to be fixed. And that Mr. Maxwell did, actually. And we're going to get through that at some point in, we're going to get through it in this class. We're going to make sure we fix this expression here because it's not complete. Okay. So this is in a nutshell what the whole chapter is all about. It's introducing Faraday Lens Law. So we need to do some problems from this. For that, I'm going to jump into. So, hey, we're going to jump into problems. How's that? So we're going to do problem 59. So I'm hoping that you guys have your book. Problem 59 is not an easy problem, okay? But it should summarize some of the ideas that I was talking about in here. Obviously, as I said before, we're going to jump into problem chapter 30, which is the induction, really, which is exactly the follow-up of this one, where we introduce inductors. And then we're going to do more examples from these 2 chapters. So, problem 59. If you look at the problems in the book, they are of 3 different levels, basically. There are problems with 1 dot, meaning that they are easy. There are problems with 2 dots, and there are problems with 3 dots, okay? Problem 54, I gave it as an exam problem in the past, something similar to it where we had it in an exam problem. So problem 54 and problem 59 are, both of them are at the same level. Problem 57 is actually 1 dot. Problem 58 is actually 2 dot, but honestly, it could have been in 1 dot because just vector products and so on and so forth. Okay, let me see exactly if I have something else to. Problem 26 is actually easy to do. So let me get into problem 59 and see how we can do that, because it really can be very helpful for us to understand this topic, this chapter. Usually, when a concept is introduced without practice, it looks kind of way out there. How are we going to even start it? But then once we apply it, once we do problems with it, it becomes a little bit more accessible. Okay. So, problem 59. It says a rectangular loop. So this is the problem. It's on page from the 15th edition, 985. Okay. It says a rectangular loop with width L. Okay. So what you have in here is you have a wire, and across that wire Let me draw it with a thicker draw. And let's make it smaller. I'll minute for it to be random. Okay. As you can clearly see, there are no batteries in here. Okay, nothing. So this distance from here to here is L. Okay. This has a mass M. Okay. That's what they said. With mass M are shown in the figure. The uniform magnetic field is directed perpendicular to the plane of the loop into the plane of the figure. So I'm going to draw my magnetic field, and you can clearly see the entire region of space has a magnetic field in it. So everything is bathing inside a magnetic field, okay? One of my students in the past loved this word bathing inside a magnetic field. So it's sitting inside a magnetic field, immersed in a region of magnetic field. So at this point, there is a magnet whose north pole is on this side and the south pole is on the other side of the screen, okay? Or even like this one, it doesn't have to be. Where is the north on this guy? Here's the north. So as long as the north is pointing this way, you're fine. And you can have your loop in here next to it, okay? So it doesn't have to be a U-shaped or anything like that. It could be just be this one, okay? So obviously this one is moving in and out, okay? So as long as the magnetic field is going into the picture, then you can do that. Otherwise, this thing will move in the opposite direction. Or actually going to accelerate in that direction, I should say. So the slide wire, where is it? No, it's going to, because of Ampere's law, I mean, because of the minus sound Lens law, it's going to always slow down. So we need to find that out. So the slide wire, this is the slide wire, by the way. It's this portion. Okay, is given an initial velocity v naught. So we pushed it this way. Initially, obviously down the road, it's going to be somewhere else and it will have a different velocity v. It doesn't, the velocity should not stay the same. Okay, remember F equals to ma is also F dv over dt. So if there is a force, that force actually is changing the velocity, both magnitude and direction in general, okay? So there is no friction between the slide wire and the loop, and the resistance of the loop is negligible in comparison to the resistance R of the slide wire. So this has a resistance R. This one has a resistance R equals to 0. So in terms of resistance, that's all the resistance is happening just in this L, that's it. There is no other resistance in here, okay? Obtain an expression for F, the magnitude of the exerted force on the wire while it is moving. Look, the wire is moving this way. The magnetic field is into the picture, okay? So again, this will create a current, and I need to find the direction of the current. Again, the current is going to be counterclockwise because the electromotive force in here will push charges this way and this way. So the current, there is a current that is going to be established, and this current is pushing in this direction. So this is the direction of the current now. And that's it. If that's all you need is the direction of the current, you can find the current using the EMF divided by R, because this looks like this. It looks like as if you have a battery with the resistor R. So how much current is flowing through the circuit? Actually, the battery is pointing in the opposite direction now because the current is actually flowing this way. So if I use Ohm's law, it says the EMF is equal to Ri. From here, I is equal to the EMF over R. That's it. So all I need to do is find this EMF, and the EMF is given by minus the change of the flux with respect to time divided by t. And the minus is just for the direction. I already accounted for the minus. So what I'm saying in here, take it in absolute value. So which brings me to a very, very important aspect of this whole solutions of using Faraday Lens Law. The first step is ignore the signs. Just find the magnitude. Once you find the magnitude, pay attention to the direction using the minus sign. Since I already used the minus sign to find which way the current is going to flow. Let me explain again. As the wire is moving this way, the area is increasing. You guys see that? If the wire is moving toward the empty side, then the area is increasing. So the flux is increasing in magnitude into the picture. So Faraday Lens Law says it needs to compensate by generating an electric field so that its magnetic field pointing outside compensate for the ever increasing field lines going in. So for that, the magnetic field needs to be out. Since the magnetic field needs to be out, the current must be going counterclockwise. So we have found the direction. So all the business of the negative sign is to find the direction. Once you find the direction, you don't care about the negative sign anymore. Do not put a negative sign in here. It's going to be a double jeopardy. It's like minus minus. Your language instructor, the English person, will be annoyed by this kind of double negations. Okay, so this is exactly the same thing in here. So if he or she is here, they would also be extremely annoyed with it, which is true in this case, because you already used that negative sign to find the direction of the electric current. And it's going in this direction, counterclockwise. Since you have found it, and I flipped the polarity in here of this EMF as if I have a battery. Of course, I don't have a battery, and that battery is coming from Faraday Lens Law, then I'm in business. Then I need to find what this flux is. So the flux is just the product of the area times the magnetic field, BA. Because B is fixed, so it's come out of the integral. So the flux phi of the magnetic field is just this quantity. And the area in this case, the width is not changing, L is not changing. What is changing is this direction. And it's changing with the rate V. So this is going to be equal to d phi with respect to B. With respect to T in magnitude. And that is my EMF is going to be B times L times V. I did not really do any derivations or integrations or anything like that, because B is constant, so the flux of the magnetic field come out of the integral. L is the width of the area, does not change, it's the same. What is changing, it's actually length and length x, but I need to find its derivative because I need to find the derivative of the entire flux. B is fixed in magnitude and direction, so I don't have to worry about that derivative of that. L is fixed in magnitude and direction, so I don't have to worry about it. The only thing that I have to worry about is this direction, and that is changing at the rate of V at any given point in time. So this is the EMF now. So the current now, I can find it to be I is going to be BLV over R. So that is my current. I need to find the force. Now what I have in that current now, I have a wire of length L sitting in a magnetic field, and that wire has a current L in it. If I go back to chapter 27, actually, the force then from chapter 27, let me find it in here since I have my notes in here. The force on a wire that has a current running through it, it's I times L times B. I times L times B. So in this case, the force exerted on this charge, this element of wire, is going to be the current I times L times B. I need to find the direction of this force though, because if I'm going to use F equals to MA, I better find that direction of the force. Okay. Let's go back into the wire. The current is going up, the magnetic field is into the screen, so the force is actually out on this side. So this is the force now that we're talking about. So this force is actually pointing in the opposite direction. So in other words, it's slowing down this wire. So this force is pointing in this direction. because again, I, which is the direction of L, L is the direction of I, I'm sorry, and the magnetic field is going into the screen, so the force is actually in the opposite direction. See how difficult these things are because of this cross product here, and cross product there, and everywhere, until you, at the end of the day, you find you go full circle basically of cross products. If you're not paying attention to the science, you're going to get into a lot of trouble with the magnetism, especially. Okay, so the force, we know its direction, it's opposite to direction of motion. The wire is moving this way, the force is actually throwing it down. And its magnitude, now since we have I, all we have to do is multiply it by BL, and then the expression for the force, since we were asked to find it, this force then is going to be I is equal to BLV over R, so it's going to be B squared, L squared, over R, and this R is the resistance, by the way. This is the ohmic resistance times V. So this is the ohms resistance. This is in ohms, really, okay? So that is what question A is. Question A is obtain an expression for F, the magnitude of the force exerted on the wire while it is moving at speed V. Show that the distance X that the wire moves before coming to rest is this expression. Okay. Obviously, the force is slowing down, although it had an initial velocity V naught, but it's going to slow down until it comes to a rest, until it comes to a stop. Okay, because this effect is actually slowing this particle in here. I have actually done a video that probably I should send you the link to it too, for the eddies that form in wires. Okay, they slow down. This is like an eddy. Okay, so let me apply Newton's law now. For the wire, it says M times dV over dt is equal to F. Since I have the direction of motion, since I have the velocity, this F is actually in the negative direction with respect to V. So this force is actually a negative value if this is positive, okay? So the acceleration is in the opposite direction, A, okay? So this is the direction of the velocity. So this is actually a decelerating force. So I'm going to write it as M dV over dt is equal to minus this expression, minus BL squared over R, where R is the resistance times V. Obviously, I need to integrate this expression to find the velocity. So this velocity as a function of time needs to be integrated. So what I'm going to find in here is dV over dV, which is a typical expression that we do at this point, is equal to minus B squared L squared over R, and M in the denominator, I have to divide by the mass, times dt. So what I did in here is divided by the mass, the entire expression. I divided by V also, the entire expression, and then multiplied by dt. So multiply by dt and divided by M times V, okay? So this is the expression you're gonna find. When you integrate on the left-hand side, what's the integral of dx over x? You guys know? Because the integral
of x.
Yes. Except now we're dealing with V. So this is the ln of V. And remember, we started with V naught at t equal to 0. V was equal to V naught. And we're looking for an expression at some time t. So at some time t, the velocity is just some function of Vt. So if I integrate this expression from 0, the velocity was V naught, and then at some point in the future it's Vt, this must be equal to minus B squared L squared over MR, and this is the integral of dt from 0 to t, so it's just t. Now, if I exponentiate everything in here, first of all, I need to be careful in here with this log. I have to write it down as ln of V minus ln of V naught, where V is, I'm assuming it's just some function of time t, is equal to minus B squared L squared over MR times t. ln of the difference, if you guys remember from the properties of the natural log, ln of a minus ln of b is ln of a over b. Does everybody remember that expression from your calc class or from your properties of the natural log? Yes? Very good. So this is actually ln of b over b naught is equal to minus b squared L squared over mr t. Now if I exponentiate everywhere, so this is the exponential of the natural log, which is just the argument of the log, because it's the entire operation of the natural log. And this is the exponential of minus b squared L squared over mr t. Okay. So the velocity v will be v naught exponential of minus b squared L squared over mr times t. In other words, this is an exponential slowdown. So at t equal to infinity, this rod, or what did they call it? Slide wire will stop. Because if I take t going to infinity, exponential of negative infinity is 0, and v will be 0. So ultimately, it's going to come to a stop. So the question is, and we did not answer that question, is show how far it's going to move, basically. We need to find how much it moved, okay? X is the entire displacement. We don't mean by it the position. We mean by it the displacement. So it started from some point, which we're going to assume it's the origin. Now it moved the whole distance x. X is actually this displacement. So let's find the displacement. Again, v, if you remember, is dx over dt. So that means dx is simply equal to v dt, which means the x, which is the entire displacement, is the integral from t equal to 0 to infinity. When t goes to infinity, this thing comes to a standstill. Okay, so that is basically what this whole expression is. So let's find it. So x is the integral from 0 to infinity of v dt. And v, we just found that exponential times v naught. So x, the displacement, this is the entire displacement, not just some finite displacement. This is not at instant equal to t. No, at infinity, after you wait a long time, because we know after we wait a long time, this comes to a standstill because the exponential goes to 0. So if we do that, and we're careful with the algebra, the integral of v naught, which is constant, from 0 to infinity of the exponential of minus b squared L squared over mr t dt. The exponential, the integral of the exponential is just the exponential, except that you have to pull the reciprocal of this expression. So it's going to be a minus mr v naught over b squared L squared, the exponential from negative of the negative b squared L squared over mrt, evaluated between 0 and infinity. At infinity, this is 0. So what you have in here, you have 0 minus, at 0, it's 1. The exponential of 0 is 1, the exponential of infinity, negative infinity is 0. So this entire expression is just multiplied by -1, and the negative cancel, and the actual displacement will be a positive displacement because that's how we really want it, because it's a displacement. So it's mr v naught over b squared L squared. You see, the difficulty really is not in Faraday Lens Law. If you're worried about Faraday Lens Law, Faraday Lens Law was here. Where is she? Here, to find the EMF. Then we used Ohm's law to find the current. Then we use an expression from actually Lorentz force to find the force on a wire. So this is a Lorentz force actually. And then we used F equals to ma, where most of the bulk of the work was. So if this gives you a hard time, it's not because of physics 2. It's because of physics 1, actually, not because of physics 2. Physics 1 is the one where we have to go and solve this mdv over dt and do this exponential and things with that. So let me check again to make sure that this is the expression. Yeah, it's mv naught r over L squared B squared. That's exactly what we were supposed to find. So this is the total displacement before it comes to a standstill, okay? So in other words, I can use this expression if I know what V naught is, if I can basically measure the mass is, find the resistance using an ohm meter, L in here, I can actually use this expression to find the strength of the magnetic field just by measuring the distance x, okay? So if tomorrow, for example, you want me to find how much is this thing is, this magnet is, all I have to do is just create a loop wire in here, loop, then bring a rod that I know its resistance. If I don't know its resistance, I can measure it using an ohm meter. This actually can act as an ohm meter, if you can clearly see in here. It has an omega on top of it, so I can find the resistance of that wire, that rod. And if I can find how much initial velocity I'm going to give it, and it should not be hard basically to measure the displacement over time. If I can find, using spring actually, if I can basically tailor the string so that it gives me a specific force, so I know how much kick it's going to give me. So I can be careful with all of these things. I know how L is using a ruler. So the only thing is in how big is B in Tesla. So I can use an experiment to find what B is. If I measure the distance the whole rod basically will travel before it stops, I can find X. From there, I'm going to plug in everything, and I'm going to do this as an experiment actually to measure the magnetic field in Tesla. Now, let me summarize again this problem, 59, so that you understand that difficulty is not really in Ampere's law. It is, in a sense, if you're not careful with it. I'm not Ampere's law, I'm sorry, Faraday's law. Faraday's law has two components in it, two essential components in it. The first one is finding the direction, and the direction has to be in such a way, because as this wire is moving in this direction, in the direction indicated, okay, there are more and more field lines encountered. So at this point, I have 1, 2, 3, for example. If it moves to this point, there will be 3 more. If it moves to this one, there will be 3 more, so and so on and so forth. Each time I'm going to pick up few more field lines while it's moving this way. So there are more and more field lines going into the picture. So it needs to create its magnetic field to remove those additional ones, to basically compensate for the ones that are going in by having its own magnetic field pointing up outside. And the magnetic field pointing outside of the screen will need a current actually going counterclockwise, okay? So now I have resolved the direction in terms of this EMF. If I know the direction of the EMF, I know the direction of the current too, because if I'm going to replace that circuit by an equivalent circuit from previous chapters, then this is the EMF. It needs to be pointing in here to generate its current in that direction. Now I have that direction of the current going up in that direction. Now I'm going to go invoke chapter 27 from the Lorentz force, basically, where we derived an expression for how much force is exerted on a wire sitting in a magnetic field. That force is given by the product of L, cross product of L. What L is has a direction of the current. Since the direction is pointing upward, then the L needs to be pointing upward. The magnetic field is going into the screen, so the force in this case needs to be pointing away, slowing down the rod. So I know the direction of the force. How much its magnitude? Then it's just a product of the current times the L times the magnetic field. And how am I going to find the current? Using Ohm's law. Ohm's law says that the current in this case, which is a simple circuit, is just the EMF over R. So now I have the current. I have also the force. Since I have the current, plug into the expression, and now all of a sudden I have an expression for the force in magnitude. I know its direction. It's opposite to the velocity. So I need the negative sign. And that is, at that point, physics 2 ends here. Okay. This physics 4A takes over. So we know the force, We know Newton's law. We're now doing physics for A. This has nothing to do with physics for B. Namely, F equals to ma, making sure the signs are correct, and now dealing with this integral in here, integral of dx over x, which is the natural log, picking up some properties of the natural log, and then the exponential in there. And now you have to note that this thing, if you wait a long time, this rod needs to stop. And it's, of course, intuitive enough. It needs to stop because the force is actually opposite to the velocity. So if you give it an initial kick, it's going to move, but it's ultimately going to slow down. If you give it a kick in the opposite direction, so you will have less and less field lines. So the current actually needs to compensate for the decreasing field lines. So it needs to push the current in the clockwise direction. So in other words, the force will be actually in the opposite direction and we'll slow it down still. So we're going this way or that way. This acts like friction, really. Okay, it's opposite to the velocity. Whichever way the velocity is pointing, this is slowing down the motion. Okay, and it's going to stop after an infinite amount of time. Since we were asked to find really how far it needs to move, so we needed to find the displacement. The displacement is just the integral from 0 to infinity of the velocity dt. And the velocity is at that exponential. When you integrate it from 0 to infinity, the upper limit will give you 0 and the lower limit will give you actually 1. But don't forget the integral of, when you're dealing with integrations, exponential of some constant times t dt is simply equal to minus, so this is the integral, is minus, what is it, 1 over a exponential of negative at. So this is the antiderivative in general, okay? So with this example, I know we are almost out of time. We're going to meet again on Wednesday, where I'm going to introduce the concept of inductors. There is some stuff that I did not talk about. The eddies, for example, I know I mentioned them briefly. We're not going to do a lot of problems with them, honestly, in here. And like I said, there is a demo that I'm going to share with you that I did actually in the past with the eddies. They have importance in terms of applications. There is metal detectors, and when a car comes to a stop in a red light, for example, and how what's going on with it and how it triggers the red lights and so on and so forth. The bottom line is, this is the chapter in a nutshell, everything that we need. The next chapter, which is the inductance. We're going to use this one actually and introduce a new device that is going to be part of our circuits, which is an inductor. An inductor, capacitor, a resistor will be our components for an AC circuit, which is the next big deal after this stuff in here. We're building toward the next big deal, which is a current. So if the next midterm, the next exam, since we still have a few minutes to talk about it, it's going to be heavy on chapter 31, actually, and 32, okay? And maybe also chapter 27, okay? Or 28 to be more specific, okay? So chapter 31, where the AC circuit is going to play an important role in it. Chapter 32 also, where the solution of Maxwell's equations in vacuum and the electromagnetic waves are also going to be very, very important. So between these two, you have a big exam coming next down the road, namely exam 2, okay? There will be probably minor stuff from the previous chapters, well, maybe chapter 28 or 29. I mean 28 or 27. 29 is going to be really part of this stuff in here too, okay? We're going to introduce the AC current and how it's made, which is just this law basically applied, and use the AC current down the road, and basically hopefully we'll get into the RLC circuit and the RC circuit and everything else that has to do with it. Sounds good, doesn't it? Sounds exciting, doesn't it? Yes, no? Okay, at least some of you are excited about this stuff as I am. Okay, I'm gonna stop now here. So let me stop the recording and I will see you guys on Wednesday, okay?
See you on Wednesday.